All right, let's dive into a topic that's, well, it's pretty much a cornerstone of modern statistics and machine learning. We're talking about the maximum likelihood method. Now, I know that sounds super technical, but trust me, the idea behind it is incredibly intuitive. It's all about letting our data show us the way to the best possible model. It is a fundamental tool, and by the end of this, you're going to see exactly why it's so powerful.
And before we really get rolling, I want to give a huge thanks to Dr. Mahdian. He's the one who prepared all the fantastic material we're going to be walking through today. Okay, let's jump in.
So, what is the big problem we're actually trying to solve here? Well, it doesn't matter if you're in science, engineering, or finance, you run into the same basic situation over and over again. You've got data, measurements you've collected from the real world, and you've got a mathematical model that you think describes how that data came to be. The real question is, how do you bridge that gap? How do you take a messy cloud of numbers and use it to build a model that actually works?
This slide just lays it out perfectly. Over on the left, that's our data, the stuff we observed. In the middle, that's our model. I want you to think of it like a machine with a bunch of knobs and dials on it. We call those knobs parameters, and we usually lump them together in a little variable called theta. Now, every single time you twist those knobs to a new setting, the machine spits out a different result, which you see on the right. So the core problem, the whole reason we're here, is to figure out what the single best setting for those knobs is, the one that makes our model's output match the real-world data we collected, and we can't just eyeball it. We need a solid, justifiable reason for our choice. Okay, so to solve this, maximum likelihood estimation, or MLE, asks us to just completely flip our way of thinking. It's not just some formula. It's a whole new perspective on how our model and our data relate to each other. It takes us from just fitting a curve to really thinking in terms of probabilities.
Right, so normally you might think, how do I draw a line that gets as close as possible to all my dots? MLE flips that question completely on its head. We take the data we actually collected, that single point on the slide, and we treat it as a fixed fact. It happened. Then we ask a much more interesting question. Of all the possible models I could have, which one makes the data I actually saw the most likely, the least surprising? Look at those different bell curves. Each one is a different model, a different setting for our theta knobs. For the gray curves, our data point is way out on the edge. It's a long shot. Getting that data point would be super improbable. But look at that orange curve. Our data point is right near the peak. A model with those parameters would say, yeah, that's exactly the kind of data I'd expect to see. The whole idea of MLE is to pick the model parameters that give the best probabilistic explanation for the data we're holding in our hands.
And that brings us to the main tool for this whole thing, the likelihood function. You see it written as L of theta given our data z. Now mathematically, this looks exactly like a probability density function, but our viewpoint is flipped. In a probability class, we'd say, okay, the coin is fair, and then ask, what's the probability of getting 3 heads? The model is fixed. With likelihood, the data is what's fixed. We already have it, and the model's parameters, theta, become the variables we can change. So the likelihood function answers the question, for any possible setting of my model's knobs, what was the probability I would have seen the exact data that I did?
This image just nails our goal. I want you to imagine that likelihood function as a giant landscape, a mountain range. Every spot on the ground is a different setting for our parameters theta. And the altitude, the height of the mountain at that spot, is the likelihood. So the maximum likelihood principle is as simple as it is powerful. Our job is to be a mountain climber. Find the absolute highest peak in that entire landscape. The coordinates of that peak, the specific values of theta that get you to the top, that is our maximum likelihood estimate. It is, by definition, the set of parameters that makes our data the most probable. That's our entire mission.
Okay, the principle is crystal clear, right? Climb the mountain, find the peak. Simple. But how do we actually do that? It's easy to talk about a landscape of probabilities, but how do we build this function and then find its highest point? Let's get into the practical toolkit.
So in the real world, it boils down to 3 steps. First, you take a guess at your parameters, and you use your model to see how wrong it is. You calculate the prediction errors. Second, if you can assume those errors are all independent of each other, then the total probability of seeing all of them is just the probability of the first times the probability of the second times the third, and so on. This massive chain of multiplication is your likelihood function. But big problem. Trying to multiply a million tiny numbers between 0 and 1 on a computer is a recipe for disaster. The result just vanishes into 0 because of rounding errors. And that's where step 3 is our hero. We take the natural logarithm of the likelihood. Because of how logs work, the log of a product becomes the sum of the logs. So we've turned an impossible multiplication problem into a simple, stable addition problem. Finding the peak of this new log likelihood function gives you the exact same answer as the original, but it's 1,000 times easier to actually compute.
Now, to make things even more practical, we can make an assumption that's super common and usually pretty reasonable. In a ton of real-world systems, sensor noise on a robot, little variations in a factory, daily stock market jitters, the errors tend to clump around zero in that classic bell curve shape. You've seen it a million times. That's the Gaussian, or normal distribution. And making this one assumption is the key that unlocks a really deep and useful connection.
And here it is. This is the big aha moment. When you take the math formula for that Gaussian bell curve and you plug it into the log likelihood function we just talked about and you simplify everything, something magical happens. All the messy parts of the formula, the pi, the square roots, they all turn into constants that don't actually change where the peak is. To make the log likelihood as big as possible, you are left with only one thing to do. You have to make the sum of your squared prediction errors as small as possible. This is a huge deal. It means the method of least squares, something many of us learned as a basic curve fitting trick, is actually just a special case of this much bigger, more powerful maximum likelihood idea. MLE is the deep theory that explains why minimizing squared errors is often the right thing to do. It's because you're secretly maximizing likelihood, as long as you assume your noise is Gaussian.
So we've got an intuitive idea and a practical method that even connects to stuff we already know. But is that the whole story? Is it just a fancier way to do least squares? Not even close. Now we have to ask the big question. Why do statisticians and data scientists treat maximum likelihood estimation like it's the absolute gold standard? What are the theoretical superpowers that really make it special?
This gets us into a much deeper idea. So we have our estimate for the parameters. Great, but how good is it? If we went out, got a whole new batch of data, and did this all over again, will we get the exact same answer? No way. There's always going to be some randomness. So how much wiggle is okay? And more importantly, is there some kind of universal speed limit, a theoretical boundary on how precise any estimate could possibly be? To answer that, we have to talk about variance. Just look at these two targets. On the left, you've got a low variance estimator. Every time you run it, you get an answer that's tightly packed around the bullseye. It's precise, it's reliable. The target on the right, that's high variance. The shots are all over the place. It's unpredictable. Now, if you're building a guidance system for a rocket, you definitely want the estimator on the left, right? You need precision. You need low variance.
So the question is still out there. Is there a limit to how low that variance can get? Is there a rock bottom? And the answer is a huge yes. It's one of the coolest results in all of statistics, and it's called the Cramér-Rao Lower Bound. The best way to think about this is like a fundamental law of physics for estimation. It sets a hard floor. It says, for this problem, this is the minimum possible variance any unbiased estimator can ever achieve. You literally can't do better. It's the ultimate benchmark, the gold standard.
So, how does our friend, the maximum likelihood estimator, stack up against this ultimate gold standard? Well, as we collect more and more and more data, as our sample size grows, the MLE basically wins 3 Olympic gold medals. First, it's consistent. That means it's guaranteed to eventually zero in on the one true value of the parameter. It finds the right answer. Second, it's asymptotically normal, which means the errors it makes around that true value start to look like a perfect, predictable bell curve. And third, and this is the big one, it is asymptotically efficient. This means its variance actually goes down and hits that floor. It achieves the Cramér-Rao lower bound. So for large datasets, MLE isn't just a good method. It is provably mathematically the best possible method. It is as precise as anything can be.
Wow, okay, we have covered a lot of ground. We started with a really basic problem. We introduced a whole new way of thinking about it with probability. We built a practical toolkit, and then we found out it has these incredible theoretical properties. So let's just zoom out for a second and put the whole picture together. I mean, this is really the complete package, isn't it? You've got the core principle. This simple, intuitive idea of picking the model that makes your data most probable. You've got a practical implementation. Most of the time, this just means minimizing your errors. You've got proven theoretical power. With enough data, it becomes the most precise estimator possible. Game over. And finally, broad applicability. This isn't some dusty idea from a textbook. This is the foundation for countless advanced methods in machine learning, economics, system identification, you name it. It's a complete, elegant, and seriously powerful framework.
So we've established it. Maximum likelihood is the ultimate data-driven approach. It lets the data do all the talking. But that leaves us with one final, very interesting question to think about. what if the data isn't the only thing you know? What if, from say, a past experiment or just the laws of physics, you already have a hunch about what the parameters should be before you even see your new data? How could you combine your prior beliefs with the new evidence from the data to get an even smarter answer? Well, answering that question, that takes us into the amazing world of Bayesian statistics and methods like map estimation. And that, my friends, is a story for another time.